Circular functions are functions that can be made periodically. That's going to be a word you might hear if you look up other things about these types of functions. But this unit circle, like we wrote down on our unit circle, can be created with x and y coordinates that represent cosine and sine of the angle theta or s of the arc length. Okay? We wrote this already on the unit circle we created ourselves, so you do have all of this information down here. So really this front page just becomes a formality. You know all of this. You know that sine is y, cosine is x, and the tangent is the ratio sine over cosine. And just because we have the idea of those bow tie reference angles, we're able to apply this topic beyond just quadrant 1 into the rest of the quadrants. But let's talk a little bit more in depth about the values of these circular functions. Circular functions of real numbers are obtained in the same manner as trigonometric function values in radians. This applies to both methods of finding exact values, which we now have around a unit circle, and calculator approximations. But make sure you notice that we may now be working in radian mode in our calculator, which also means you'll have to go back and forth because we may work in degrees and we may work in radians. But with your unit circle here, and I've taken a picture of a unit circle and put it down, but when you have your paper plate unit circle, it's going to help you answer questions like exact values of different angles. If I wanted the exact value of sine of 3 pi over 2, all I do is look at the angle in the point where the angle 3 pi over 2 exists. So what is the y coordinate here? -1, which means sine of this angle 3 pi over 2 is -1. What's the x coordinate?
0.
Which means cosine of 3 pi over 2 is 0. If we do tangent, remember tangent is sine over cosine. So if I do this and show a little bit of work, I would have sine over cosine. Uh-oh. Can you divide by 0?
Nope.
No, so how do you answer this?
Undefined.
Undefined. So the unit circle itself becomes very, very helpful because we know all those coordinate points we wrote down are the values of those trig functions. Let's keep going again. Let's say I ask you, look at your unit circle, like hold it in your hands if you don't know these things already. Use the unit circle to find the exact values of cosine 7 pi over 4. So look for the angle 7 pi over 4. Did you find it? Should be on a pink line. What is the x coordinate of that point?
Square root 2 over 2.
So cosine of 7 pi over 4 is square root 2 over 2. What about the sine of 7 pi over 4?
Negative square root 2 over 2.
Negative square root 2 over 2. I wanted the y coordinate point from that, coordinate point.
Tangent is 1.
The tangent would be 1. It didn't ask for that, but yes. Now this makes sense. If we think back to what we learned for All-Star Trig class, we're in quadrant 3, correct?
Yep.
I mean, just kidding, 4. 4 is the C quadrant, so cosine is positive. That means sine and tangent would be negative. Check. Use the unit circle and the definition of tangent to find the exact value of tangent of negative 5 pi over 3.
Oh, that's the green line.
Okay? 5 pi over 3 would be on a green line, but if we're going negatively,
Oh, we gotta go clockwise.
we got to go clockwise. So just like we counted 5 green lines, including pi, to make 5 pi over 3, count clockwise 5 pi's over 3 green lines. What is the tangent of negative 5 pi over 3? Maybe let's back up and let's work this out. What's the y coordinate of that point?
Radical 3 over 2.
Square root 3 over 2. What's the x coordinate?
1/2.
1/2. Oof, we got fractions over fractions. What was the rule again? Keep, change, flip. So we keep square root 3 over 2. We change, we flip. The 2's cancel, and we're left with square root of 3. Remember on the back of your unit circle, I had you write down all those tangent values?
Yeah.
Look at the one that had pi over 3. What did we write down as that answer? Same thing, because any pi over 3 version is going to be square root 3. It just may be negative square root 3, depending on what quadrant you're in. This is actually in quadrant 1, so it's positive.
Okay.
It says use reference angles and radian to degree to conversions to find the exact value of cosine of 2 pi over 3. Okay. Cosine of 2 pi over 3. Find 2 pi over 3 on your unit circle.
Yeah.
What is the x coordinate there?
Negative 1/2.
-1/2. The end. See how nice this unit circle is for knowing exact values? This is like the table you guys had in chapter 2, but like better.
Oh, okay.
Because it's the entire unit circle. As long as you remember which one's which, you're good to go. Now, my friends with bad handwriting, this next page is for you.
Yay.
Because I printed a whole unit circle here for you.
Let's go.
So if you don't trust your handwriting, this is your unit circle. Let's add my color scheme here so it makes sense. We used pink for pi over 4. So let's add pi over 4 and 45 degrees in pink. Okay. All of that is going to be pink. Every pi over 4 multiple will also be pink. It's going to look a little janky because of the way that all these numbers are, but you get it. Pink, pink. This is 315. Oh, boom. The next color we used was green. That was your pi's over 3 or 60 degrees. So here's the pi over 3, 60 degrees. Uh-huh. That's the color of your unit circle for that angle, is it not? If you're having to share because I had you put back your markers already, so sorry. I will pause after this and let you finish coloring. Just wanted my room to be clean. And then we use blue for pi over 6 and 30 degrees. So every multiple of pi over 6 that doesn't reduce, bless you, to another angle, we will color in blue. You get it. So again, I prefer using the paper plate because it's more fun to hold. But if you don't trust your handwriting, you do have this reference here for you. The only one you can use on the test for me, though, is your paper plate. So if you needed a new one because you wrote so badly you can't read it, there's another resource here for you to create a new one. The only other thing we added to ours was the All-Star Trig class positivity checker. So you can do the same thing as well. Do you notice that there are no degree symbols for any of these angles? Do you see that?
Yeah. Wait, what?
That means we are in radian mode.
Oh, joy.
So set your calculators back to radian mode, which means you could just reset them. Second plus 712.
Oh.
Uh-oh. And then we're going to just calculate the calculator approximation for each of these angle measurements. If you type into your calculator in radian mode, cosine of 1.85, what do you get?
Negative 0.275. Are you wanting a fraction?
No, it won't turn into a fraction because it'll probably have a square root in it at some point, so it won't rationalize. It's an irrational number.
Is that why sometimes they don't turn it into fractions because they have radicals?
Correct.
Oh, wait, why can't a calculator do that?
I don't know. I'm sure there's some reason with like coding because it depends on what square root you take. But square root numbers are irrational numbers that cannot be rounded. Or like they don't ever come out to like a pretty number. They're just like continue on forever and ever. So that's why they're a problem. I don't know why the calculators haven't gotten smart enough to do that. But I don't know.
What would make them so?
I'll think about it. Yeah. Okay, what about the cosine of 0.5149? 0.8703. Oof. But what about cotangent? How did we type cotangent into the calculator before again? Cotangent. Yeah, cotangent is the reciprocal of tangent. So we're going to do 1 over the tangent of 1.3209. And when we do that, we can actually get the value of cotangent.
0.2552.
0.2552. And then this is the reason I keep asking these questions. How do we type in secant? 1 over cosine, because secant and cosine are reciprocal functions. And when we compute that, 1 over the cosine of that angle in radians, what do you get?
A decimal.
I'm holding.
Negative 1.0243.
3, yeah, correct. So using our calculator is always going to give us an approximation as opposed to an exact value. So if you see the words exact values, it's probably going to be something that comes from your unit circle, because it should be a value we know without having to use the calculator and get these decimals that come from irrational numbers that we would know automatically in our unit circle. Now we can reverse the processes above to use a calculator to determine the angle that gives you that particular trig value. These keys, we've used these before, correct?
Yes.
Inverse sine, inverse cosine, and inverse tangent.
Yep.
They do not tell you the reciprocals. They are the inverse functions. Their output is an angle. I had to ask that question because I haven't taught this in some of my classes, so I keep forgetting what class knows what. Sorry. So the question will say something like this. Approximate the value of the variable, this case s, in the interval between 0 and pi over 2 if cosine of s is equal to 0.9869685. Quick question.
Yep.
What quadrant is this if we're going between 0 and pi over 2?
Pi over 2, sir?
1.
1.
Quadrant 1. Okay, so we should be getting an angle that's in quadrant 1. Now, because we're doing this on our calculator, we're not going to get a cute number like we would if we could do this on our unit circle. But we don't recognize this number as a number from my unit circle, so we're going to have to use the calculator for it. That means we're going to solve both sides so that s is by itself by taking the inverse cosine of this ratio, 0.9685. That's the trig value as opposed to the angle. What is the angle that gives us that trig value?
0.2517.
Very good. Now, we do need to make sure that this is actually between 0 and pi over 2. So in your calculators right now, just do pi over 2 by itself. What's that number?
1.570.
Is our value of s smaller than what you just said?
Yeah.
Yeah,
570.
1.570. This is the inverse cosine of this value. We're just, oh, good point. We're just making sure our answer, this angle, is actually between 0 and pi over 2. And it is. It's bigger than 0 and smaller than 1.5 something.
Yeah.
Okay. This next one says, find the exact value. Whoa, whoa, whoa. Exact value means we're going to use our unit circle. The first one said approximate. We could use our calculator.
Yeah.
Find the exact value of s in the interval from pi to 3 pi over 2. Pause. What quadrant is this between pi and 3 pi over 2?
3.
Quadrant 3. We have those black quadrant numbers, they're called the quadrantial angles, listed on our unit circle. Okay. What is the value of the angle if tangent of s is equal to 1?
Oh, that's the one.
If we're doing tangent, flip your paper over. We put all the tangents on the back.
Square 2 over 2.
Hold on. What is the angle that we highlighted the pink number 1 on the back for?
225.
Hold on. On the back of the paper, what angle is that?
45.
45.
Yeah.
45 degrees is in quadrant 1. Flip your paper back over.
Yeah.
What is the angle on the pink line, the 45 line, in quadrant 3?
Quadrant 3?
225.
225. 225 degrees. Let me see. Where did I put my unit circle so I can show you what I'm doing here? Oh, this is not the one I made right now, but it's a unit circle. Let me pull this up. Okay, I don't have mine color-coded, but on the back, pi over 4 is always going to be equal to 1. But we didn't want pi over 4, which is in quadrant 1, right? This is pi over 4. I want the version of this angle in quadrant 3, between pi and 3 pi over 2, which is how many degrees? 225, or in radians, in case that's what it's asking for. How many radians is that? Same line. What was the radian measure on your unit circle? 5 pi over 4. Depending on how they want you to answer, you can answer in degrees or in radians. That's the nice thing about our unit circle. It's very versatile. Last but not least, we have this example that uses a bunch of trig functions to model a legitimate thing in real life.
It's a lot of words and numbers.
It is, but read the question because it's really not as hard as it seems.
Okay.
It says the angle of elevation theta of the sun in the sky at any latitude L is calculated with this crazy formula.
Okay.
But watch, these are the things that I need. I need theta. I need this value d, which I happen to use twice. I need a value L, the latitude, which I will use twice. And then I need some omega value.
Omega.
That is the Greek letter omega. Fun fact. Okay, the Greek letter omega is the number of radians that the Earth has rotated through since noon. When theta equals to 0, d is the declination of the sun, which varies because the Earth is tilted on its axis. Sacramento, California has a latitude of 38.5 degrees. Oh, but look, I already changed it to radians for you. 0.6720 radian. We're going to find the angle of elevation of the sun at 3 p.m. on February 29th, 2012, when at that time, d is approximately 0.1425 and omega is approximately 0.7854. The reason I told you not to panic is because this formula requires d, L, and omega. What were we given in this problem? Oh, okay, so this is a plug and chug question. If we were doing this, the sine of theta would be equal to the cosine of negative 0.1425, that's d, times the cosine of 0.6720 radian, times the cosine of, yeah, I know, sound like a broken record, 0.7854, plus sine of negative 0.1425, close parentheses, times sine of, listen, that's what the formula says to do. Whew.
Oh my goodness.
Here's what I want you to do. Right now in your calculator, because that's a whole lot to type in, I want you to go ahead and give me that answer. So cosine of that number times cosine, plus sine, plus sine. Go ahead and type that in.
4, 5.
You should at this point have a value for all of that crazy stuff. Cosine, sine, yes?
Yes.
Here's the thing, that doesn't answer my question because the question was, what is the angle? So to get theta out of sine, I'm going to have to do the inverse sine of all of that. But I know you know the shortcut where either you press second enter, which will type A and S in your calculator, which means take the previous answer and plug it in. Or I also know y'all know to toggle up and press enter, yeah?
Yeah.
So we're taking the inverse sine of all of that mess that we just got. And when you do that, you should get 0.4773 radians. Did you get that?
Yes. When should we get?
0.4773?
Okay,
Now here's the deal. In this real life question, if somebody asked you what's the angle of elevation and you said 0.4773 radians, they'd probably look at you like you were crazy. Let's answer this in degrees, which is generally how we answer angle of elevation questions. So let's convert this into degrees. What's the conversion factor?
Oh,
I don't know, 180 or 180. I think it's 180.
If it's in radians, already, it's the 180 over pi. So put 0.4773, or if it's longer than that in your calculator, use the more accurate number, multiply by 180, divide by pi. In degrees, this is 27.3447 degrees, which may be a more accurate way to tell someone the answer to this particular question, since that's the accepted unit for this type of thing. If you got lost in there, I will come around just at the end of these notes